Welcome everyone to the section of the course on object detection. The goals for this section are to understand a variety of object detection methods, and we're going to slowly build up to more complex methods as we go along in this section of the course. So we're going to start off with template matching. Template matching is probably the simplest idea behind object detection, and all it does is it simply looks for an exact copy of an image within another larger image. Then we'll move on to just general detection methods like corner detection, which is looking for corners, edge detection, which expands on this idea to find general edges of objects, and then grid detection, which combines both concepts to find grid-like patterns in images, which is really useful for lots of applications. Then we'll move on to talking about contour detection. Contour detection allows us to detect foreground versus background images, and also allows for detection of external versus internal contours. For example, grabbing the eyes and smile from a cartoon smiley face and realizing that those are internal contours versus the external contour of the actual circle that holds the eyes and the smile. And we'll be working with that exact example later on. Then we'll move on to general feature matching, and this is going to be one of the more advanced methods of detection, specifically detecting matching objects in another image. And it's going to work even if the target image is not shown exactly the same in the image that we are actually searching. Then we'll talk about the watershed algorithm, and it's an advanced algorithm that allows us to segment images into foreground and background, and it also allows us to manually set seeds to choose segments of an image, and we'll be working with both those concepts. Then we'll move on to facial and eye detection. We'll be using Haar cascades to detect faces in images. Note that this is not yet facial recognition. We're only going to be able to detect if there's a face or if there's a set of eyes in an image. We won't be able to yet say whose face or whose eyes they belong to. Later on, when we talk about deep learning, then we'll talk about actually recognizing unique faces or unique images. At the end, we'll have a really cool project assessment where we're going to build a full computer vision application that can actually blur license plates automatically given an image. So it'll see an image, detect where the license plate is, and then we'll apply our own blur to that license plate. So it's going to be this really awesome application. All right, let's get started by talking about template matching. We'll see you at the next lecture. Subset. So we're going to see an example of that in just a little bit. Welcome back, everyone. In this lecture, we're going to go over template matching. Template matching is probably the simplest form of what you could refer to as object detection. All it does is it simply scans a larger image for a provided template by sliding that template target image across the larger image. So if you have a picture of someone's face, then what you're going to do is you're going to take the picture of that face and then slide it across the entire image until you find a match. Keep in mind, it pretty much has to be an exact match. So that means you already have the image provided for you, and it's just a subset. So we're going to see an example of that in just a little bit. Now, the main option that can be adjusted when it comes to template matching is how are you actually making that comparison? Is it a direct one-to-one per pixel, or is there another method? So all of the methods that are used in template matching, they're based on some sort of correlation. So here we can see the different methods that OpenCV has available. These are things like the squared difference, the normalized squared difference, the correlation coefficients, and so on. And there's the mathematical formula for how they're actually calculated. What we're going to do is we're going to explore how well each of these works, and we're going to have a target image. So what we're going to do is we'll have a target image of a dog's face, and then scan a larger image to see where we actually find the match of the dog's face, and then highlight it. Okay, so let's explore template matching with OpenCV. I'm going to head over to the Jupyter Lab. Okay, here I am at a Jupyter Lab notebook. I went ahead and did the main imports that we usually do. That's CV2, NumPy's NP, and setting up Matplotlib. Next, what we're going to do is actually grab the full image that we're going to be searching for our template. And that's going to be cv2.imread. And inside of the data folder we provide, go ahead and read in the sammy.jpg file. And then we'll also correct its color so that we can show it. We'll say cv2.cvt color, and then pass in the full image and say cv2 color underscore bgr to, whoops, that's not the right one, to RGB. There we go, bgr to RGB. Run that, and let's go ahead and show off the image. And there it is. So we've seen this image before. It's a picture of my dog, Sammy. Next, what we're going to do is upload the template image. So this is going to be a subset of the larger image you're searching. So what we will do here is say face is equal to cv2, image read, and this one is data and it's called Sammy face. And same thing here, we'll say CVT or CV2, CVT color. We'll take that face, and then we'll say CV2 color underscore BGR to RGB. And now let's show Sammy's face. And there we have it. So two important things to notice here. One is that this picture of my dog's face, Sammy, the dimensions of it, if we check out the shape, are 375 by 486. And this is actually the exact size and shape of the face of Sammy within this larger image. So the full image is quite a bit larger. We see shape here, we see 1367 and 1025. So something that is basically restrictive of template matching is you should have already the exact image you're looking for, which kind of defeats the purpose of general object detection, but that's why this is one of the simplest forms of object detection. You already have part of the image that you're looking for in the larger image. So all this really is going to do is it's going to take this face that I have here, this subset template, which is Sammy's face, and then it's going to just go line pixel by pixel scanning the image until it finds a match. And the match is going to be based on how it's making its comparison. And there's different ways we can make that comparison and see whether or not we have a match. And those are the things we're going to be experimenting with. Okay, so one last note I want to do is within this lecture, we're going to be using the eval function. And I want to show you quickly what it does in case you've never seen it before. If you've already seen the eval function, you kind of skip forward. But just in case you haven't seen it yet, as you probably know, there's built-in functions in Python like sum. So if I take the sum of a list here, it's 6. Now, what I cannot do is do something like this. Say my string is equal to sum, and then try to call sum or my string in this fashion. That doesn't really make any sense, right? Because this is a string, that's not actually the function here. However, with this specialized eval function, I can actually evaluate this string as if it was a function. So I can say evaluate my string, and then it gets back, okay, I evaluated the string, I have a matching function, I think it's the function sum. So then I can do the following. I can say my func is equal to eval my string, and now my func has been assigned the evaluated string here, sum, so I can actually call it as a sum. So I should be able to say 1, 2, 3 with my func and 6. So that is essentially a way you can directly transform a string that matches a built-in function, such as sum, and then actually run that. So we'll be using this eval because we're going to have a list of strings, and then we're going to evaluate them all to transform them into OpenCV functions. It's just a little cleaner to do it that way instead of calling each one manually. So keep that in mind. If you haven't seen that eval function, that's all it's doing. It's just evaluating that string for a function call. Okay, let's move on. All right, now for the next step, I'm actually going to copy and paste the list from our notebook because there's a bunch of different methods here and we're going to be using them, and I want to make sure I spell them all correctly. So go ahead and find a cell in the provided notebook from our zip file that has the list of methods. So here are all the methods you can use for the actual comparison of the template matching. So there's a bunch of different codes here. You can check out the documentation. We actually showed a picture in the slides before this of the equations that each of these follow, but we're just going to run through them and see how they perform. Notice how they're all strings, and that's why we actually went over the eval function because we're going to evaluate each of the strings into a function. Okay, so let's begin. We're going to make a for loop that goes through each of these methods and then uses template matching with that particular method. We will say for m in methods, and the first step we're going to do is create a copy of the image. So this will create a copy of the full image. That way we don't accidentally mess up because we're going to be drawing a rectangle on the full image for wherever we think we found the match. So we first create a copy of the full image. Then I want the actual function I'm going to be using. So I will say method is equal to eval m. So what that means is as we actually loop through the string methods here, I'm going to evaluate that string, so then it's actually a function. Okay, so we have eval m, and then the way you actually perform the template matching is the following. We say the result, or res, is equal to cv2 match template. Make sure you spell that right. You should autocomplete that. And then you pass in the full larger image. So in our case, it'll be full copy. And then we're going to pass in the smaller image that we're scanning for. In this case, it's the face of the dog. and then you pass in the method you want to use to actually have the selection criteria of whether or not we think there's a match. Okay, so there we have full copy, face, and method. Now just really quickly, I want to show you the result of what this match template looks like. So outside of this for loop, I'm actually going to select and comment this all just to make another cell. So let's run this. We'll say full, face, and then I'm just going to choose one of these methods. So let's grab this guy. So let's actually show you the way this works. We'll say my method is equal to eval that string, and then we'll pass in my method here. Okay, so if you run this, what happens is it takes this full image, it scans it for where it thinks it found a template match with this face based off the method you provided. In our case, it's CV2 TM CCOEF, or the coefficient there. So what does this result actually look like? Well, I can plot this out and say PLT imshow, and you'll notice that it's essentially a heat map. And what this does is it has higher values where it thinks it found the highest correlation of where the match actually occurred. It depends on the actual method, and the two methods that use squared differences, these ones, TM squared difference and TM squared difference normalized, those are going to be slightly different. Those are actually going to work on where it finds the minimum value, so keep that in mind. But for the rest of them, it's where it finds the max value. So it believes that somewhere around here, where we have that kind of white or yellowish point, that's where it believes it found the highest, most maximum value match. And that basically corresponds to the top left corner of the image. And it actually makes sense because if we take a look at the face versus the original image, it should be somewhere around maybe like 400 in Y and 300 in X of where the actual image starts. Maybe that face starts around there. And if we take a look over here, it does appear to be somewhere around like that 300, 300, or 300, 200 mark. So it looks like it's actually matching up well. So what we're going to do here is we're going to find the maximum and minimum values of this heat map, as well as the maximum and minimum value locations, and then we'll use those to actually draw out a red rectangle for where it thinks it found the match of the template. So I just want to point that out. This is what the result looks like. It's essentially a heat map, and then we're going to grab values from that heat map and use that to plot out a rectangle on the copy of the dog image. So we're coming back to this for m in methods, and then we're saying the following. So we just created a full copy, we just evaluated, we just got that heat map, and then what we're going to do is we're going to grab the minimum and maximum values from that heat map. We will say a little bit of tuple unpacking here, min value, max value, min location, and then max location is equal to cv2.min max LOC. And then we're going to pass in that result. So what this does is it takes in that heat map and it finds both the minimum and the maximum locations, and it returns them back as this large tuple that we can then unpack to find the minimum value, the maximum value, and then the min and max locations. So next what we need to do is set up everything we need to actually draw that red rectangle. And we first need to do a little bit of a check here. We'll say if m is in, actually we can say if the method, so if this method that we evaluated right here, so if that method is in cv2 tm underscore sqdif or cv2 dot tm underscore square difference normalized, then what we're going to say is that the top left is equal to the minimum location. Else, for all the other methods, we'll say that the top left of the rectangle is equal to the maximum location. And that just has to do with the way these heat maps work. For these square difference methods, because if you square something, even if it's negative, it ends up positive, then these, the way they work for the template matching, they're actually working on the minimum. So we use this method right here, this little if-else check, to say, well, where does the top left of our rectangle go? Okay, so now that we have that settled, we're going to assign the bottom right of the rectangle. And to do that, we need to actually get the shape of the rectangle. So we'll say the following. We're going to say that the height, width, and color channels is equal to the face.shape. So if I take a look at face.shape again, that's just the actual dimensions plus the 3 color channels. So all I'm really concerned about is the height and width there. And then what I will do is I will say the bottom right of this rectangle is equal to the top left indexed at 0 plus the width. And then the top left indexed at 1 plus the height. Because remember, this location value of top left, that is essentially something that looks like this. It looks like something like y comma x. So that's why we're able to do this indexing here. And actually, I kind of wrote this the wrong way. It should be x comma y, or the width plus the height. Okay, so that's what this top left looks like. That's why I'm indexing it like this. I could have just also used tuple unpacking here if that's easier for you to understand. Either way, we now have the bottom right and the top left of our rectangle. So all that's left to do is draw it onto the image and then display the image. So what we'll do is say CB2, rectangle. I'm going to pass in the full copy of my image. I'll pass in the top left. I'll pass in the bottom right. And then what it's left is what color I want this to be. So we'll go ahead and have it be red. And then the thickness, we'll have it be a pretty thick rectangle because it's a large image. So we'll say 10. And then we just need to plot and show the images. We're going to be doing a little bit of matplotlib jujitsu here. So if you're not too familiar with matplotlib, don't worry about these following commands too much. Let me get a little bit of space here by deleting these cells. Okay, so what we're going to do here is say plt subplot 121, and then plt subplot 122. And what this says is it just says, give me a plot that is 1 row by 2 columns. So we're going to have 2 images right next to each other, left and right. And then this last one, it means grab the first one, and this 2 here means grab the second one. So on the first one, we're going to show that heat map result. We'll say im show the result of the heat map, and then we'll give it the title heat map of template matching. So that's essentially the result of the template matching. And then for the second one, what we'll do is we'll say plt im show, and we'll show the full copy. Remember, the full copy now has a rectangle drawn on it. And then let's give that a title. We'll say pl title detection of template. And you'll notice some of them actually don't perform perfectly. And then we'll say plt, and we'll give it a super title, essentially a title above both of these. And we'll just have that be the actual string here. So that will be m. So we'll title everything with the method used. And then the last thing we're going to do here is, in order to actually see and not have these subtitles or subplots constantly rewrite over each other, you need to add in one more line, which is plt show. If you don't have this plt.show line, then these subplots will constantly be overwriting each other and you only get one plot at the end. So we'll say plt show, and then just for a little added spacing, I'm going to print 2 new lines after each of these pairs of subplots. Okay, so let's run this and make sure everything worked. So we're going to run this, and there you have it. So here is the method name, tmccoef. Here's the heat map of the template matching, and this is where it detected the actual template. So right off the bat, this one's really obvious. You can see here it detected a lot of matching over on this top left corner, and then that's where we drew the actual rectangle, and there you have it. It's centered right around the dog's face correctly. Then for the rest of these, it looks like it did pretty much the same thing, but you'll notice some of these, it actually detected quite a bit off. And this one, this CCORR method, it looks like it was starting to get a match here, but it found a lot of different comparisons here on the matching, and maybe it got messed up by the dog's fur, but unfortunately this did not actually detect the correct template. So you can see here, even when you have an exact carbon copy cut out, you're going to have to make sure you're using the right method for whatever pair of images you're working with. Then this one, the normalized method, you can see here, really only detected one max point. It found it nicely. And then remember, these squared differences, these are actually working in the opposite way. So it's looking for the minimum, which is why that little circle is dark there. And it looks like it found the match correctly. And then squared difference normalized here, same deal, it found the match correctly. So one of these, this guy, and it actually pretty much always tends to perform pretty badly, except in certain cases, the CCORR method. But other than that, the rest of them did find the template matching successfully. Okay, so that's it for this lecture. Again, the main components here that you have to worry about are just match template, and then the full image, what you're looking for, and then the method you decide on. And you can check out these 6 methods and see which one works the best for you. If you want to grab more information off of this result, then you can say min-max location off the result and then do whatever you want off that. Just keep in mind that square difference methods, those should be using minimums to where it found the match. Okay, thanks everyone, and we'll see you at the next lecture.